I am doing an alternate representation of standard model quantum field theory. And the first thing that most people will ask is, why? Because I'm of the opinion that the standard model is hugely successful beyond anything that we could want experimentally. Every time we've gone and tested, experimented, it's again and again precisely correct. It just matches everything that we can measure. On the other hand, when you come with theory, you have something like 18 parameters that we're still trying to figure out where they come from. They have to be input experimental, things like fermion masses, Nixon rules, things of that sort. Okay? So what I'm basically trying to do is say, well, okay, if we go ahead and represent the standard model in a way that is theoretically equivalent, can we do things in such a way that some of these parameters can be calculated? And it's still kind of a work in progress at this point, but that's the goal at this point. Now, the starting point is basically there's a statement, for example, that Steven Weinberg made, that if you have any theory that consistently combines Lorentz invariance and standard quantum mechanics, you will get a representation of standard quantum field theory. That's the defining characteristics of it mathematically. So what I basically came along with is, so okay, well let's instead of using fields without any sort of index, which are basically the standard fields we normally use the generalized coordinates in quantum field theory, and let's make them spin tensors. A spin tensor is just like an ordinary tensor that you encounter in relativity, except the basic trivial tensor is a vector, whereas the basic trivial spin tensor is a spinner. It's an object in every way like a vector, except it's got half the rotational order. That makes it useful for representing quantum objects. So, what this is essentially is it represents an operator representing the observation of some specific particle species at a classical location X. And what this is a coordinate index. Now, normally when people write that, they're either writing a Dirac index or a field index. Dirac index basically associates it with a two-dimensional spin space. That's not what we're doing here. We're essentially going to have, I'm using two fields. This kind of field, with this I'm representing fundamental fermions, like electrons and other electrons. And then basically here, the other field that I've got is a metric. Okay? And I define my metric in terms of my scattering matrix. So essentially, we take this here and we say, okay, here we have a transition where basically the metric contracted with the final state, and the initial state gives you S, which is a probability amplitude of that particular transition. When you allow these to be an array of particles so that you end up with a matrix, this becomes a matrix, and that's your scattering matrix. So, I am not claiming that all the issues with this have been straightened out. This is something that I'm working on, dealing with how to do this. But that what I've found so far is that essentially there seems to be two aspects to develop. There's the group theory aspect, and then which really is independent of the form of your equation, so of your defining field equation, so long as you insist that probability is conserved and you have completely covariant field equations defined consistently in terms of spin tensors. Okay? What I've mostly been working on lately has been dealing with using field equations very similar to general relativity to develop the geometric dynamics of this and see what I can calculate, particularly things like trying to calculate fermion masses. Well, my university has basically said, don't talk about that in specifics. So we're going to talk about the group theory aspect. Okay? Now, the defining thing about spin tensors is really their transition properties. So any transition of a field takes a general form like this. Now these are your fields, this is your transition operator, okay? Included in that are going to be any sort of physical eigenoperators like for momentum or whatever. Now one of the things is that gives these two indices. One of the things that I admit, quite admittedly, still working on is what does it mean when you have physical operators here and you're not dealing with a case where it's completely diagonal. I'll be quite upfront that I haven't yet come up with an answer to that I'm entirely satisfied with. That's one of the things I'm still working on. But when you basically have these completely diagonal, it works pretty well. You essentially then will have four components for your momentum, your position, whatever it may be. Now, this, if you notice, because let's say this, for example, represents an electron, okay? Well, we know if you rotate an electron 360 degrees, your state becomes the negative of the original state. So from that, I deduce that basically you have to allow the modulus of this particular transition operator to be either plus or minus 1 when you're making it strictly real. But here's the thing. When we develop the standard SU3, SU2, U1, we allow arbitrary phases. So the group that I'm looking at more specifically is a group where, let's say that we allow our transition operator here be represented as an exponential defined by a Taylor series of some sort of generator. Okay? Then basically what you get is, let's say that you have your square modulus of this equal to 1. Well, then basically these generators form a group, and it's a covering group that will include anything with that sort of modulus. But here's the thing, because what we're used to is invoking the Wigner's theorem and insisting that you only deal with transition operators that are modulus plus 1 or minus 1, and of course normally we take plus 1 to be able to form a group. What I basically come along and do is say, okay, here's the covering group, but physical operators are those where this modulus, not the squared one, but just the straight modulus, is strictly real. So for physical operators, what you have is that this is equal to plus or minus 1. That's where we get quantization from. Because basically what that's going to allow is just theta has to be integers of pi. You know, theta being basically kx, whatever. Okay? And so you get out you get then basically that physical operators have, are strictly quantized, just very simply coming out. Okay? Now, when you're looking at theta here, you get the usual SU3 symmetry, or SU3, SU2, U1 symmetry coming out fairly straightforwardly. The usual way that you do it. Let's say we're talking about global transitions. Well, basically, we can introduce into our field an arbitrary phase constant. Now, it's going to be basically a constant with an index. That doesn't really make a difference. It's still going to be U1. So globally when you're talking about it, you introduce an arbitrary constant phase, you get the usual U1. Okay? Then basically, we don't have to deal with non-abelian global transitions because you can always represent a global non-abelian transition by a combination of abelian transitions globally. So then you go down to dealing with local transitions, and basically, if you actually go to my profile on ResearchGate, there's an old paper that I published there that discusses an older, but kind of out-of-date version of this, where I basically construct the U2 symmetry, SU2 symmetry, sorry, from holonomic restrictions on your fields. Essentially what I developed there is I show that generalized Cauchy conditions can be used to construct SU2 entirely as if it's reference frame transformations. And essentially I go on to establish that the analogy between gauge transformations and general reference frame transformations becomes exact when you use spin tensors. That's one of the advantages of using them. Okay. And then basically go on and do SU3 in the case where these are essentially massive, because massive fields have an extra degree of freedom, and you essentially get rotation within your 3 phase. So you can essentially rotate. And again, it's pretty much just like the usual SU3. Nothing really fantastic there. The main thing here is that you're doing it in a straightforward way that makes the mathematics of it come out very simply, straightforwardly, because of the spin tensors. That's what I'm doing new. Now, okay, so far I haven't talked about anything new and exciting, so of course people are wondering, well, why do this? Okay. What I basically am trying to do is get out from here things like fermion masses. The way that I basically define things, I'm essentially constructing the usual way of representing quantum field theory as if it's doing quantum field theory in a flat reference frame where basically your metric reduces to a Minkowski metric or coordinates metric, whatever you choose to call it. And the idea is that basically, just as you cannot calculate mass of an object in its proper frame of reference or in the rest frame, so I'm saying here, well, okay, if I construct the usual way of representing quantum field theory as if it's working in the rest frame, I should be able then to get out mass calculations. I'm essentially constructing it to in order to be able to get mass calculations. It's not so much saying, it's a fine point. I'm not saying the way we do quantum field theory now is working in a rest frame. Inherently, I'm saying it's working in a rest frame because I'm defining it that way when I'm building my theory. Are there any questions so far? And basically then, when you're, okay, so that's pretty much it where you're coming from the group theory aspect, is you can go through and just in exact parallel with the usual way that we do quantum field theory, you can develop all the various groups that we know and love. And it's really just an alternate representation. The main advantage is that, I think comes in when you start putting in specific field equation. That's where I basically say, okay, let's use what we know from general relativity and construct a geometrodynamic version of quantum field theory. So basically here, we have our metric, and by basically any physical situation, inherently, the information about it inherently is contained in the metric. So, for example, a lepton field equation is basically one where you develop it as a geodesic in a space of these field operators, and you end up with an equation that looks very similar. Well, first of all, let me just define something here. So this is a scalar field, differential scalar field equivalent. Essentially, if this side, if this field, is your arbitrary field, then essentially this is a scalar non-interacting limit of it that's associated with a reference frame with an Minkowski metric. And so what you do then is you just develop things exactly as you do in general relativity. So you get a lepton field equation that looks like this. So all of this should basically be familiar to folks. Right? This is just the usual geodesic equation. This is a geodesic equation in a space of field operators, but also happens to be a lepton field equation. What I basically usually do is I will basically introduce change variables. So I'll change this then if I want to do, for example, a space-time representation. I'll essentially divide through and do change variables, get these so it's dx's, and then I'll do substitutions for momentum I get my field equation in terms of form momentum, so it's something we can calculate. And that's how we go on to actually calculate the mass. Okay? Any questions at this point? I might just boring everyone in here.
I'm wondering what inputs you put in to get those extremely specific masses that we have. What is needed to get those?
What's needed to get these?
The actual masses. I mean, you've got I have a number 12 fermions,
Right.
with 12 masses, with seemingly no explanation. So we put some input in to get some
Yes.
masses.
That's something I failed to mention, and that's my fault. When I did that paper that is on my ResearchGate profile,
Yeah.
one of the things that came out of the development of SU2 is that you can represent particles in the same field particle generation by certain sign conventions on the fields. So basically, let's say this is your field and you write it, let's say, I'm dropping the x of x for now because so we know this. Now there's two things I want to point out. One, this is comparable to other operators you have where you cannot specify exactly all the components. What makes this different from, say, a field operator is you can't say, okay, let's treat this as 4 separate fields. Due to simultaneous measurability, you will never be able to completely separate it. And one of the things is that mathematically, it tends to reduce things to essentially, let's say that you say, well, okay, I'm going to treat component 3 as not simultaneously measurable. So essentially what happens is you end up averaging overall possible values there of the component, and essentially the 2s and 3s give you equivalent equations. So you'll essentially be most of the time solving matrix equations that are 3 by 3 or whatever. Okay. And then basically what you do, if this is your electron, then basically this is your electron neutrino. And this then becomes the electron antineutrino. And so basically the way that you describe the 4 particles in a particular generation are through those particular symbols. The sign of this particular component describes the helicity. If you want it, left-handed, it's positive. If you want it right-handed, it's negative, and that's how I describe the various particles. Now, I mentioned there being essentially a matrix equation where you're dealing with matrices with three components on each side. That's how I actually get out 3 particle generations. Is when I do a mass calculation, which I wish I hadn't been forbidden to do in complete detail. What you end up with is basically solving a 3 by 3 determinant. And so because you solve a 3 by 3 determinant, you in principle get 3 solutions for your squared mass. And that's how I get outcome out of this 3 generations. And then so the combination of 3 generations with this sign convention to represent the different particles within a different field generation, that's how I represent the different field species. Does that answer the question?
To some extent, yeah.
I will admit I am still working on some of the details of this. There's still some I'm not completely satisfied with. This is more describing the work and research that's in progress. think basically one of the reasons for getting stock is getting feedback and what specifically are the problems that we dealt with, so that we, so that I have a completely thorough description.
So if you could get neutrino masses or something like that,
Right.
a few generations, before
Right.
they actually find them experimentally, that would make your work more convincing. But
Well,
if you do retrodiction of existing
Well, basically at this point, so far the work that I've come up with, what it amounts to is I essentially used a Friedman-Minkowski, Friedman-Robertson-Walker metric kind of combined with the Schwarzschild metric in order to calculate the first generation. But unfortunately, that means that my metric is completely diagonal, so I don't get 3 different solutions. I get 3 degenerate solutions. So what I actually come up with when I do that for, when I actually get the electron mass, is it comes out to the current value of the Hubble parameter. Okay, just want to say that what it's supposed to. Over to where basically you're dealing in units of Planck scale. So when you plug in Planck length for the 2r there and plug in your time a little bit, it comes out to something, what I calculated it as, once I plug in the natural units, is 0.4 something mega electron volts for the electron and 0.
So
For
you're
the
using cosmological
Yeah.
connections.
Yes.
So you feel there's a direct link between cosmology and...
I think so, yes. It kind of surprised me. I was playing around, to be honest, I was playing around with it originally. But in my paper that's, again, online, linked to one of the things was that in an older version of this I had coming out, that essentially what would happen is as the universe expands, you get it produced, essentially pumping out particles, where it's essentially, the way I describe it there is you've got, it's as if at every single point in the universe, you have a harmonic oscillator, but it's driven by cosmic acceleration. That driving of the mechanism causes, the further you get away from the person, from the observer, there's an increasing perceived potential there. And so from the point of view of the observer at the center, further you get away, you see more and more particles being produced out of the vacuum. And essentially it's a straight CP violation, which is why that paper that is completing the analogy between gauge something or other, and then the subtitle is I can't remember, you can look up the title in my own paper. Okay, it's something about basically a novel mechanism of CP violation. And essentially, so I said, well, I took that and said, well, if that's going on, then maybe one way of looking at these particles is as a bound states of essentially a vacuum universe that is expanding and having a cosmic acceleration. That's why I used the specific metric that I did. Unfortunately, at this point, the question is, I get a matrix equation that involves a metric that in principle would solve for 3 generations, but I haven't figured out what the relevant metric is to use to get a second and third generation.
So the other thing that made me think is that you've got to have some input to get some output. I just wonder what kind of input you were using.
Yeah, well, that's the
You've got 10 minutes more.
Oh, okay. So, and that's essentially what, what I'm doing, but I think the other thing that I want to get across is that my choice of using field equations based on general relativity in many ways is arbitrary. One of the things that's fascinating to me is that there's a huge degree of freedom of how you represent your field equations. And, one of the things when I first started learning the standard model was told was, because we don't have a single representation of standard model development field theory, we know therefore it is only an effective field theory. And if we had a complete theory, we'd have one single final version. I don't believe that anymore. I basically think that in principle, for any physical theory, you in principle have a huge number of representations, largely depending on our choices as physicists, how we represent things. And I guess one of the things that I'm kind of looking at inside is to what degree do we have freedom to choose and represent things in different ways, and where how big of a difference can we choose in our representation? That's the question. So, any other questions or comments?
I'm encouraged when you say that you have that much freedom, because the thing I worry about is that if special relativity theory is indeed flawed in the manner that I think it is, that can propagate into changing general relativity theory, and I hope not catastrophic consequences further on.
Yeah, well, I have to say, I tend to be an advocate of general relativity, but I'm opening to questioning. It's just like anything else. I am of the view that you have to thoroughly ground any modification we have of physical theory at every step in experiment. You have to be able to justify it. Right? One of the things I'm doing with this is, I have to admit, mostly I'm encouraged by the fact that I mostly get exactly what you would expect from the conventional way of doing quantum field theory, is because most of the time you do want exactly the same thing. You want what we observe in experiment. The question is to know when and why we can deviate from the usual way of doing things.
Well, the general relativity has multiple interpretations, isn't it?
Yes, exactly. I mean,
If you those field equations tell you nothing really.
Yeah.
Because you put in, it depends totally on the coordinate system.
well, one of the things that comes to mind for me with that is, one of the ways I was thinking, okay, so you have the field equation. Okay, if you're dealing with, with both electromagnetism and mass, well, okay, you don't plug in anything for the mass energy. You just assume that's the gravitational background. You purely do all the electrodynamics. But now if you suddenly have only gravitational forces relevant, well then you do plug in the mass energy distribution and calculate how things go. Well, it's a highly dynamic way of applying things. In this development, one of the things I didn't specify, I did specify, for me was that just in my development, I choose to construct things related to the S matrix. And I've still found that when you're representing something as curvature, you have to decide what. So the way I first started dealing with the electroweak sector was just starting with ordinary charge density as what you represent as curvature, and then using the sign conventions I mentioned to deal with neutral and anti-neutral objects.
What do you want to do this? Do you want to throw it open to questions?
Yeah, I think
Few minutes
left. Yeah.
Just, do we have any questions from the audience? Comments?
Not qualified to comment.
So this is a big problem in the standard model, with completely arbitrary parameters. Do you, apart from masses, are you looking at any other?
I'm trying to figure out things like gauge couplings. One thing, there aren't enough gauge couplings, and I'm trying to relate those to curvature.
Run unification?
I haven't, to be honest, I haven't done grand unification yet, because I figure there's quite a bit to bite off. But the main way that I personally am of the opinion that most likely gravitation is going to be emergent classical phenomena. I'm very skeptical at this point of the idea of quantum gravity.
I'm in agreement with that. I don't know if anybody else has any views on that.
Yeah, anyone want to comment there?
Anybody want to comment on quantum gravity or anything?
I tend to, the way of doing it is that in advanced general relativity, use spinor representations of those objects. And so I look at it as you've got a field space at every single classical point, and then those are kind of covered in a broad scheme by the metric dealing with classical relativity. So you've got the two going on in tandem, but the metrics are defined in very different ways. So while you be dealing with the mathematical apparatus of general relativity here, it really says absolutely nothing about gravity except the fact it's in the background.
This was also connecting cosmological and particle phenomena in that way. Would this have any bearing on this large number hypothesis concept?
I think it will, but at this moment, I'm more coming at it from the point of view of, I just think it's fascinating. I think basically, if we can thoroughly establish this connection, then things like the Hubble parameter and all that can be related to experimental measures of field particle excitations that we know to ridiculous amounts of precision, so that we can get more precise cosmological parameters that way, and then just kind of build on it. So hopefully, if we can establish this as correct, then we can get a much more precise cosmology. And I'm hoping that basically this will make a huge step forward in getting a genuine quantum cosmology.
Okay, so can we thank the speaker then? We move on to our next talk.